Hi, everyone. Welcome to this webinar on FEMA P-749, Earthquake-Resistant Design Concepts, Part B. We're going to get started in about 2 minutes. And while you're waiting, you can download the handouts using the link that we'll provide in the chat shortly. And I'll return shortly to start up the webinar. Hi, everyone. I'm Kiara McKenney, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on FEMA P-749, Earthquake-Resistant Design Concepts, an Introduction to Seismic Provisions for New Buildings. Both this webinar series and the FEMA P-749 guide are divided into 2 parts. Part A provides an explanation of the basis and intent of U.S. seismic provisions, and Part B provides a walkthrough of the seismic design process for new buildings. Today's webinar is on Part B. This webinar is brought to you by the Applied Technology Council under a contract with FEMA, the Federal Emergency Management Agency. If you haven't already, you can download the handouts using the link in the chat. And we know that many of you are interested in receiving professional development hours for your attendance today. For those who are registered and in attendance of this live webinar, a certificate documenting professional development hours will be sent by email to you within 4 weeks. If at any time during the webinar you have questions, please type them into the Q&A window that you can open from the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar, so please submit your questions as you have them rather than waiting until the end to submit them. We will answer as many questions as we can, time permitting, at the end of the webinar. And if there are some questions that we aren't able to answer live, we will provide written responses for as many of them as is practically feasible. I would now like to turn it over to Patia Scott from FEMA's Earthquake and Wind Programs Branch, who will provide a brief introduction to today's webinar. Patia, please go ahead.
Thanks, Kara. Good afternoon. My name is Patia Scott, as Kara said. I'm a civil engineer in the Earthquake and Wind Programs Branch at FEMA, and it's my pleasure to welcome you to today's webinar on Part B of FEMA P-749, Earthquake-Resistant Design Concepts. As part of our responsibilities under the National Earthquake Hazard Reductions Program, FEMA supports activities to reduce future earthquake losses. The primary way we do this is through the development and publication of technical design and construction guidance products, as well as through the support of training and related outreach efforts, such as this webinar. FEMA supported and worked with the Applied Technology Council to develop this webinar to provide a tool that communities and other entities could then use to encourage greater protection from earthquake hazards, thereby reducing future earthquake losses. Understanding the basis for the seismic regulations in the nation's building codes and standards is important for design professionals, students, building owners, and operators, and many others. So we hope you enjoy Part B of this webinar. Back to you, Kira.
Thank you, Patia. So now I'll tell you about your incredibly accomplished presenter today. Ron Hamburger, SE, is a consulting principal with Simpsons, Gumpertz, and Hager. He has nearly 50 years of structural engineering experience, including design, education, construction, failure investigation, and development of engineering guidelines and code provisions. He served as chair of the Building Seismic Safety Council's Provision Update Committee from 2001 to 2009, chair of the ASE 7 Standards Committee from 2011 to 2022, as well as a member of the AISC Committee on Specifications, the ASE 41 Committee, and the AWS D18 Committee. He has personally investigated the damage from 12 major earthquakes and widely disseminated the lessons learned from these events. In recognition of his work in developing and improving the nation's building codes, he has been awarded the National Council of Structural Engineers Association's James DeLahey Award, the Structural Engineering Institute's Walter P. Moore Award, ASCE's Newmark Medal, and was elected to the National Academy of Engineering in 2015. Ron also served as primary author for the FEMA P-749 document on which this webinar is based. I'd now like to turn the webinar over to Ron. Ron, please go ahead.
Thank you, Kiara, and welcome everyone, and thank you for joining us. We hope you find this webinar interesting. Today we're going to be talking about Part B of the FEMA P-749 document, which specifically goes into a review at a very fundamental level of technical criteria contained in U.S. building codes, and specifically the ASCE 7 standard for seismic design of structures. The document is arranged in two parts, Part A and Part B. Mike Griffin gave a similar webinar a week ago on Part A, and the focus of Part A is really for the general public, people who do not know much about earthquakes and how we design for earthquake resistance. Part B, which I'll be talking about today, is intended for design professionals, specifically civil and structural engineers, architects, and in particular, students and engineers and architects who are young in their careers and hoping to learn some of the fundamental concepts. We're going to start our webinar today with a few poll questions. And so the first of these, and we hope that you'll respond to them, is I'd like to understand the technical background of the audience I'm working with. So please tell us if you're an architecture or engineering student, a practicing architect, a practicing civil or structural engineer, or some other type of engineer, for example, mechanical or electrical.
Great, and it looks like most people have already responded, so I will just take a few more seconds before ending the poll. All right, Ron. The results are...
It looks like most of us are practicing civil or structural engineers. Great, thank you. Our next poll question asks you to rate your experience level of seismic design. Have you never designed a structure for seismic resistance? Do you have some experience in seismic design? Or do you think that you have extensive experience?
Okay, it looks like most people have already answered, so just a few more seconds to get your answers in. And Ron, I'm going to go ahead and close the poll, and the results are showing.
It looks like the most of the folks attending, more than nearly 60%, have some level of experience in seismic design, and about 30% extensive level. So this webinar is not really focused at this audience, but if you pay attention, and I hope you will, I have a few things I think you'll find interesting. One, I'll be talking about the new ASCE 722 standard, and some of the differences in this updated standard relative to the one we've been designing to for the past 5 years or so, ASCE 716. So you may find that interesting. And you'll also get an understanding of what is in the FEMA P-749 document and how useful it may be for use as an educational tool for some of your colleagues and younger engineers and architects on your staffs. So the FEMA Part B of the FEMA 749 document starts off with a review of the basic structural design process and spends a good deal of time giving a primer on basic structural dynamics, because as most of you are aware, almost everything we do in earthquake-resistant design is based on structural dynamics. The guideline goes into a discussion of the dynamic behavior of single degree of freedom structural systems, and primarily linear elastic single degree of freedom structural systems. For those of you who are not familiar with this, a system is said to be linear and elastic if, when you apply twice the force to the structure, you get twice the deformation or deflection. And if you remove the force, the structure comes back to an at-rest position that looks like what it was before the force was applied. There is no damage, and the structure is capable of responding in this manner as many times as you wish to apply the force. If you take such a linear elastic single degree of freedom structure and you apply a force to the mass located at the top of the structure, and then you release the force, the structure is going to oscillate back and forth in sinusoidal motion, such as is shown in the graph to the right. And the amount of time that it takes the structure to make one complete oscillation from one position within its deformed shape back through to a negative of that position and forward again to the original position is called the period of the structure, the natural period of vibration, and it's measured in seconds. And we can see that for the cartoon that I have here, this particular single degree of freedom structure has a period of about 1 second. It's relatively easy to calculate the period of the structure. It's equal to 2 pi times the square root of the mass of the structure divided by the structure's stiffness. And we more commonly use weight rather than mass. And so it's also equal to 2 pi times the square root of the weight divided by the stiffness times the coefficient of gravity, 32.2 feet per second squared. An idealized single degree of freedom elastic structure will have no damping. And if displaced to a deformed position and then released, it will vibrate back and forth forever. The reality is that most structures have some degree of damping or energy dissipation inherent in them. And so if a structure has non-zero damping, it is displaced to a deformed position and then released and allowed to oscillate, the damping will basically leach energy from the system, and slowly, over a period of a number of cycles, the structure will come to rest. The damping inherent in a structure is a function of its materials of construction, and also the level of response that the structure undergoes. Structures that have low levels of deformation tend to exhibit relatively low levels of damping. Structures that are pushed to extreme levels of deformation will exhibit a lot of damping. In structural engineering, and in particular in seismic engineering, it is typical to express the level of damping present in a structure as a percent of the critical damping. As a review, the level of damping that we call critical is that amount of damping that will bring a structure, when it's displaced to a deformed position, to rest exactly in 1 period's worth of time and will not oscillate at all. The graph that you see on the left here is a graph of displacement versus time for a structure that has 1 second natural period and is 100% critically damped. The other 2 plots here shown on the right are for the same SDOF structure with a period of 1 second. In the middle graph, I'm showing a result for 5% damping, and in the graph on the right, one for 25% damping. You can see that the greater the damping is, the more quickly the structure comes to rest. And in the building codes, in the ASCE 7 standard, we typically assume that buildings and structures have 5% of critical inherent damping. If you have a single degree of freedom structure, such as the one I've been talking about, and you want to understand its response to an earthquake ground motion, the most direct method of doing that is basically by integrating the equation of motion, shown on the lower right-hand slide here. In the equation of motion, the quantity u of t is the displacement versus time function of the ground. The quantity x of t is the displacement of the structure's mass relative to the ground at a point of time t. The stiffness K and damping C are coefficients and properties of the structure. And by integrating this equation numerically, you can determine what the displacement versus time of the structure relative to the ground is, and also what the force in the structure is. I've done that for a single degree of freedom system structure, having different periods, 1 second, 2 second, and 4 second. And I've analyzed the response of those structures to the 1949 El Centro ground motion. And what you can see when you look at the response of each of these structures to that ground motion is the structure largely tends to be responding as if it's in simple harmonic motion, meaning it has been deformed and allowed to release and shake back and forth at its fundamental period. So we can see for the 4 second structure here, it basically oscillates back and forth at a period of about 4 seconds. The 2 second structure oscillates back and forth at a period of about 2 seconds. The 1 second structure does this back and forth at a period of about 1 second. And literally what's happening is the ground shaking is plucking the structure as it kicks the base back and forth, and then the structure responds in free vibration to that plucking induced by the ground. This provides us with a convenient tool for evaluating the behavior of structures and predicting their response to earthquake ground motion without having to exercise that complex integration that I showed you on the previous slide. And that tool, of course, is called response spectrum analysis. The plot that you see here on this slide is what we call an acceleration response spectrum. And I constructed this acceleration response spectrum by conducting analyses, such as the ones that I just showed you, for structures having many different natural periods of vibration, and plotting on the vertical axis the peak acceleration experienced by the mass of the single degree of freedom system in response to the ground motion, all the same ground motion, as a function of the period of the structure. If someone has done that work for you and developed a response spectrum, and you want to find out what the response of your structure will be to the ground motion represented by that spectrum, it is fairly easy. For my example that I'm using here, I have a structure with a period of 2 seconds. I simply enter that response spectrum plot at the period of 2 seconds, read across to the vertical axis, and find that this structure will have about 0.2 g of peak spectral acceleration response. I can then find the maximum force in the structure using Newton's third law as force equals mass times acceleration is just equal to 0.2 times the weight of the structure. That is assuming that the spectral acceleration is expressed as it is here in units of fractions of the acceleration due to gravity. If I want to find the maximum displacement, I can do what I always do in statics, which is take the force and divide it by the stiffness of the structure, or a very convenient tool that actually allows you to do this without any analysis at all is to use the formula on the lower right and compute the displacement as the fundamental period t squared divided by the quantity 4 pi squared times the spectral acceleration for the structure times the g, the acceleration due to gravity. And in fact, when analyzing complex built structures like high-rise buildings, I will frequently get a first estimate of the structure's response just by doing this quick calc and not doing any analysis whatsoever. Everything I've been talking about so far relates to the earthquake response of a structure that's capable of responding in a linear, elastic manner. The fact is, as Mike told us last week, that for reasons of economy, and because earthquakes are very rare events and most structures that we design will never see their design earthquake, rather than spending the money and societal resources to design structures so that they can experience design events without damage, we actually design them with the intent that when they are subjected to design earthquake shaking, they will experience a lot of damage. And that damage exhibits itself in the form of nonlinear structural response. The graph that you see on the right here is a cartoon of the response of a structure, single degree of freedom system structure having the same period as the linear structure shown on the left-hand graph, but capable of resisting nonlinear hysteretic response. And we can see that that can be actually beneficial in a number of ways. First of all, the peak displacement exhibited by the nonlinear structure is about 3.5 inches, which is less than the 4.5 inches exhibited by the linear structure. And also the peak force that the structure sees is about 100 kips in this case, as compared to 175 kips for the linear structure. And so we use this beneficial behavior of nonlinear response both to reduce the amount of force that the structure will experience, reduce the amount of displacement it will experience, and design more economical structures. And this, of course, is inherent in everything we do under the ASCE 7 seismic design provisions. With that basic understanding of structural dynamics, we can talk about the overall seismic design process. It starts with determining the structure's use or occupancy, and knowing the structure's use and occupancy, its risk category. Based on the building site, we determine the design ground shaking spectrum. We determine the building seismic design category based on the ground shaking spectrum and parameters derived from that spectrum and the risk category. Next, we select an appropriate seismic force resisting system. Could be a moment frame, a bearing wall, a braced frame, etc. Next, we design the seismic force resisting system, considering the effect of structural irregularities, if any are present. We design the non-structural components in the building by assuring they have adequate anchorage and bracing to the primary structure. This presentation is going to go through each of those steps at a very fundamental level, as they are embodied in the ASCE 722 standard, which will be referenced by the 2024 International Building Code, which will be adopted by most cities, counties, and states in the United States. We'll start by looking at how we determine the seismic design category. Table 1.5.1 of ASCE 722 specifies things that are called risk categories. The risk categories are a categorization of buildings and structure types related to the amount of risk they pose to society if they fail. ASCE 722 has a very simple table of risk categories. The building code, the IBC, has a much more complex and much more detailed table. Here we're going to focus primarily on the ASCE 7 criteria, but of course, if you are designing in a community that has adopted the IBC or another building code, you should be using the risk categories as defined in that building code. There are 4 risk categories. Most structures that we design are going to be in risk category 2. This includes stores, offices, homes, warehouses, most places where you and I live and work. Risk category 1 are structures like barns and greenhouses that are not normally used for human occupancy. And in the building codes, we're generally willing to accept a higher risk of failure of such structures simply because there's a lower risk to life if the structures fail. The performance intent for seismic resistance in ASCE 7 and the building code is actually identical for risk category 1 and 2 structures. And the primary intent of the ASCE 7 provisions is simply that there is less than a 10% chance of collapse in the event that the structures experience what we call maximum considered earthquake response shaking. MCE shaking is a very rare level of shaking. In most parts of the United States, MCE shaking has an average return period on the order of a few thousand years. And the specific return period at a given portion, at a given site in the United States is going to depend on the seismicity in that area, but typically it's going to vary from 1 to 3,000 years. Risk category 3 structures embody structures with very large occupancies. For example, high-rise office buildings that may have 5,000 or more occupants in them during the day. They involve structures with housing people with limited mobility, schools, nursing homes, prisons. It includes structures that contain potentially hazardous materials. Because the people that are in some of these occupancies are less able to get out of a damaged building than most of us, and because there are significant consequences to release of hazardous materials, ASCE 7 seeks to provide somewhat better performance for these structures. So for risk category structures, it's 3 structures. ASCE 7 targets providing less than a 5% chance of collapse in MCER shaking and limited potential for release of materials due to damage. The final risk category is risk category 4. This includes structures that are essential to post-earthquake response and recovery, or which contain high volumes of hazardous materials, which could harm a great many people if released. For these structures, ASCE 7 seeks to provide less than a 2.5% chance per year of collapse given MCER shaking, and provide an intent to remain functional following most earthquakes that are likely to affect the structure. Earthquake response spectra, whether they are design level spectra or maximum considered earthquake spectra, are going to be different for every earthquake and at every site. However, they do tend to have similar characteristics depending on what the nature of the site is and its distance from the fault creating earthquakes. This makes it possible to draw what we call smooth design spectra. The intent of smooth design spectra is basically to iron out the little peaks and valleys that occur from one earthquake motion to another, and to provide a relatively simple representation of the variation of ground motion with period that envelopes the average response obtained from all likely earthquakes that will affect a structure. The design response spectrum, which is what we derive our seismic design forces for structures are, is going to be different for each site. It's dependent on the regional seismicity, how likely it is earthquakes will occur at the site, the magnitudes of those earthquakes and their frequency of occurrence, the types and depths of soil of different types at the site, the distance of the site from faults, the depth of occurrence of earthquakes along those faults, which can vary from near surface to many kilometers deep, the mechanisms of fault rupture. All of these things affect the types and character of spectra which will be experienced at the site. The procedures for determining design response spectra and the parameters we derive from those spectra in ASCE 7 are contained in Chapter 11. The procedures start by determining the site class. The actual procedures used to determine the site class are actually contained in Chapter 20. There is also within ASCE 722 something that we call a default site class, which can be used for design when you are unable to follow the procedures of Chapter 20 and don't know what the actual characteristics of the soils at the site are. Once you've determined the site class, you determine the spectral response ordinates. The way I recommend that you do that is by using a free tool that's available from the American Society of Civil Engineers. If you go to Google or your favorite search engine and type in ASCE hazards tool, it'll bring you to a link that will allow you to get to that tool. And by entering relatively simple data, which I'll take you through in a moment, you can produce your design spectrum and the design spectral quantities. It is also possible, as it has in the past, to follow the procedures of Chapter 21 and do a site-specific development of design spectra. Once you have the design spectra, you determine the design spectral response parameters per Chapter 11. First step in the process, determining the site class. As Mike Griffin discussed last week in this webinar, the level of shaking that a site will experience is a function of the types of soil that are present subsurface, typically in the top 30 meters or 100 feet. Rock and hard rock tend to produce relatively low amplitude shaking. And as soils become softer, they tend to produce higher amplitude shaking and shaking that has energy content at longer periods. And we represent these effects in ASCE 7 by referring to the site class of the soils. In past editions of ASCE 7, it was possible to determine the site class based on a description simply of the types of soils present. So if a site had soft rock, that would define you as site class B. If a site had modestly dense or stiff clays, it would define it as site class D. And there were other similar qualitative descriptions that would enable you to determine the site class. Geotechnical engineers could determine the site class by the number of blows per foot using standard penetrometers that they use when taking soil borings and do site explorations. A difference in ASCE 722 is that we no longer permit classification of sites based on qualitative descriptions of the types of soil that are present, nor do we permit it to be determined based on average penetration blow resistance or N counts. Instead, we require that you have an estimate of the shear wave velocity of the site in the top 30 meters, given in feet per second. So that is one important difference in ASCE 722, is you now have to have the shear wave velocity profile in order to determine the site class. Another important difference in ASCE 722 is that there are some new site classes. In ASCE 716 and earlier editions of the standard, we only had site classes A, B, C, D, E, and F. ASCE 722 introduced some intermediate site classes B, C, C, D, and D, E. I see there's an error on the slide. The lower green rectangle should have been drawn around D, E. These intermediate site classes are provided to allow a transition between the rather abrupt changes in spectral shapes between B and C, C and D, D and E, and to allow us to design more economical structures when we're designing for a site that has intermediate site class characteristics. An example of how to determine what the site class for a site is, given that you know the shear wave profile for the site is given here. In this hypothetical site, bedrock is located about 60 feet below the surface of the site, and the rock has a shear wave velocity of 3,000 feet per second. Above that is a 20-foot layer of dense sand with a shear wave velocity of 1,600 feet per second. And above that, a stiff clay with a shear wave velocity of 600 feet per second. To determine the average shear wave velocity for the site used to determine site class, we use the formula that you see in the upper right-hand corner here, executed with the calculation shown in the formula below it. We find that there is an average shear wave velocity for this site of just over 1,000 feet per second, which would put us in site class D using this procedure. If you don't have the shear wave velocity profile for a site, it is possible under ASCE 722 to use what we call the default site class conditions. And what the default site class conditions consist of are the spectral response acceleration values that are the worst for either site class C, CD, or D at any period of the structure. Go now to the ASCE 7 seismic hazards tool. As I said, you can get this by doing a Google search, or you can find it at the URL I show on this slide. Once you bring the hazard tool up, you tell the tool which edition of ASCE 7 you want to use. You can use it for 722, 716, or 710. You locate the site that you're working on. You can do this by typing in the address. It uses a Google Maps search feature to find the lat and long of the site. If you have the lat and long, you can use that directly, or you can use a pin feature and basically drop a pin on the map that you see here in order to locate your project site. Once you do that, you input your site class, your risk category. You tell the tool what hazards you want the data for. You can do it for seismic, wind, atmospheric icing, tsunami, etc. And you hit the button to bring up the results, and you get a summary such as you see here. And what the summary shows you is the data that you put in, including the location of the site on a map so that you can verify you didn't have an input error. It then goes in and provides you, if you're interested in seismic, both the maximum considered earthquake response spectra on the right and the design spectra on the left. It does this using a format that's called the multi-period response spectrum, which also is new in ASCE 722. What the multi-period response spectrum is, it's basically a table of the spectral values of the two spectra at 20 different periods, ranging from peak ground acceleration or 0 seconds to 10 seconds. It also gives you the old format, 2-period response spectrum that we've used in ASC 716 and earlier editions. In addition to giving you a plot of the spectra, it gives you discrete values for the peak ground acceleration, the S sub MS, S sub M1, S sub DS, and S sub D1 values, the S sub S and S sub 1 values, the transition period T sub L, that are used in different parts of the standard to determine design forces and displacements. For this example here, we find we have an S sub DS value of 1.16 and an S sub D1 value of 0.6. By the way, I ran this example for the headquarters office of the Seattle Building Inspection Department. The old editions of ASCE 7 had a series of maps in chapter 22 by which you could determine your S sub S and S sub 1 values, and there was a procedure by which you could use F sub A and F sub V coefficients to convert those S sub S and S sub 1 values into the S sub DS and S sub D1 values needed for design. That no longer exists in ASCE 722. We want you to use the ASCE seismic hazards tool to determine these values. But if you don't know what your site class is, there is one set of maps in chapter 22 for the so-called default site class that will give you S sub MS and S sub 1 values for the default site class, and you can determine the S sub DS and S sub D1 values by taking 2/3 of the mapped value. And those values, S sub DS and S sub D1, can be used to construct the old 2-domain acceleration response spectrum that was used in the earlier editions of ASCE 7 and is still used in ASCE 722 as the basis for the equivalent lateral force technique for determining seismic forces. I do want to show you this for that site that I showed you previously. The spectra on the left is the multi-period design spectrum for site class C. And you can see that for a structure having a period of 2 seconds, it has a spectral design value of 0.3 G. If you were to use the default site class for this site, you would find a value of 0.5 G. So there is a very significant penalty to using the default site class in terms of the amplitude of the seismic forces that you end up designing for. I therefore don't recommend its use except for very small projects where seismic design forces are not likely to have major economic impact on the design. Once we've determined our seismic spectrum, design spectrum, for the project and the S sub DS and S sub D1 values, we can determine the structure's seismic design category. ASCE 7 assigns seismic design category structures based on their seismic risk. That is, the consequences of their failure. There are 6 seismic design categories in ASCE 722, just as there were in earlier editions of the standard. They range from A to F, with A representing structures that rate the least seismic risk, either by occupancy or as a result of where they're located, and F representing structures that have the highest risk to society. The seismic design category affects many aspects of the design, including the types of structural systems that can be used, and also the analysis procedures that can be used to determine the design seismic forces on the elements of the seismic force resisting system. Once you have the seismic design parameters, S sub ds and S sub d1, you go into chapter 11 of ASCE 7, and there are two tables, table 11.6-1 and 11.6-2. You go into each of those with your values of S sub ds and S sub d1 and determine what seismic design category you are in. If the value of S sub 1, also obtained from the ASCE 7 seismic hazard tool, is greater than or equal to 0.75, then that bumps your risk category up. So if you are in a site where normally for risk category 2 structures, you have a spectral acceleration S sub 1 of 0.75 or greater, and you are an ordinary occupancy structure, normally categorized as seismic design category D, you would be in seismic design category E. And if you were in a risk category 4 structure on a site with such ground motion, you would be bumped to seismic design category F. And that's taken care of by text in the standard rather than these tables. Once we know what our seismic design category is and what our seismic design parameters are, we can proceed to design the structure. The first step in designing the structure after we have the design category is to select the type of seismic force resisting system we're going to use. The available seismic force resisting systems depend on the seismic design category, the structure type, that is building or non-building structure, and the structure's height. Buildings, of course, are the things that most of us design most of the times. Buildings are defined in the building code as a structure that is typically enclosed and has a primary intended use of human occupancy. Common structural systems for building type structures are load-bearing walls, braced frames, moment frames, and dual systems. The criteria for design of building structural systems are contained in Chapter 12 of ASCE 7. Folks that work in industrial design and in transportation structures will find themselves designing structures defined as non-building structures. There are two types of non-building structures. There are non-building structures that have structural systems similar to building structures, that is moment frames, braced frames, dual systems, load-bearing walls, etc. And then there are non-building structures that have structural systems unlike buildings. The requirements for non-building structures are found in ASCE 7, Chapter 15. And here you see some types of non-building structures that have structural systems that are not like those of buildings. After you determine the ground motion for the site and the type of structure, you select the seismic force resisting system. Seismic force resisting systems are categorized by the material type and the behavior. For example, for bearing wall systems, there are timber bearing wall systems, concrete bearing wall systems, masonry bearing wall systems. And these systems can be further categorized as being ordinary, intermediate, or special. Special structural systems have extensive detailing requirements, and because of those details are capable of experience extensive nonlinear or inelastic behavior without losing load carrying capability. Ordinary systems have relatively few detailing requirements, and as a result of that, may not be able to provide the same reliable nonlinear behavior. As a result of that, ordinary systems must be designed for higher seismic forces than intermediate or special systems. Buildings and structures classified as seismic design category A can use any structural system, including structural systems that don't appear in the standard. Buildings classified as seismic design category B through F must use one of the specific seismic force resisting systems or combinations of systems provided in Table 12.2.1 of the ASCE 7 standard, or in tables contained in Chapter 15 for non-building structures. Looking at Table 12.2.1, blown up at the bottom here. This table, by the way, is 4 pages long and contains nearly 100 structural systems. We can see that structural systems are defined by their basic type, for example, bearing wall, moment frame, etc. The material of construction, in the case of bearing wall systems, concrete, masonry, etc. And then the level of detailing, ordinary, intermediate, or special. The table lists not only the systems, but the permissible R values, C sub D coefficients, and any limits on the height of the system depending on the seismic design category. If an NL appears in the table next to the system name, that means for that seismic design category, there is no restriction on the use of the system. Other categories will have height limits shown in this excerpt of the table as either 100 foot or 160 foot, and it's not possible to use the systems for structures that are taller than that. As shown here is Table 12.21 compared with tables 15.4-1 and 15.4-2 that show similar requirements for non-building structures. Generally, the R, C sub D, and omega 0 values for non-building structures are less restrictive than those shown in Table 12.21. First of all, because industrial types of structures have proven themselves better able to resist earthquake response than building structures for a number of reasons, and also because there are typically fewer people at risk if those structures fail. In determining the design seismic forces required for a structural system, it's necessary to determine if the structure is regular or irregular. ASCE 7 requires structures provided with sufficient strength so they can resist specified earthquake forces in combination with other loads. The specific combinations of loads, including dead and live loads, are contained in Chapter 2, and the seismic forces are amplified for irregular structures. In seismic design category A, the procedures are simplest for determining the required seismic forces. Structures in seismic design category A are required to have adequate strength to resist 3 different types of forces: global seismic response forces, continuity tie forces, and specific forces for anchorage of walls to diaphragms. The global seismic design forces are computed simply as 1% of the building weight at each level, applied in each of 2 orthogonal directions, as shown here. These 1% of the weight types of forces are not actually expected to be earthquake forces. Rather, they are a nominal load that is used to verify that the system has a complete lateral force resisting system, able to experience some level of wind force, seismic force, or for that matter, even the forces associated with a truck or an airplane flying into the structure. The continuity tie forces are equal to 5% weight of the smaller piece of the structure tied to a larger piece, illustrated in this diagram here as a little balcony or an eye cantilevered off of a floor diaphragm under ASCE 7 and seismic design category A. It is required to have sufficient tie back to the main structure to resist 5% of the weight of that element. In seismic design categories B, C, D, E, and F, there are 4 methods available to determine the design forces on the elements of the seismic force resisting system. The simplest and most commonly used is the so-called equivalent lateral force technique. This is contained in section 12.8 of the standard. There is a still further simplified method of the equivalent lateral force technique available in section 12.14 of the standard. That's available only for relatively simple, low-rise structures that have seismic force resisting systems that are relatively rigid. And the simplification available in section 12.14 is that you don't need to determine the drift of the structure because it is a relatively rigid system, and the vertical distribution of the forces in the structure is somewhat simple. There is also available a modal response spectrum analysis technique, a linear response history analysis technique, and a nonlinear response history analysis technique. The linear response history analysis technique is new in ASCE 716, and it is not the one that we have commonly used in the past. Rather, it is intended to give very similar seismic design forces to that which is determined by response spectrum analysis. The specified earthquake forces are typically lower than the forces that the design earthquake will actually produce in a structure that is capable of responding in a linear manner. This is because of the benefits of nonlinear response, as I described earlier. The magnitude of the specified forces and how they are determined depends on the seismic design category and the values of those C sub D, R, and omega 0 coefficients I showed you earlier in the table. This in turn is dependent on the type of structure and the type of element within the structure. The procedures used to calculate the lateral forces in seismic design categories B through F are similar, although for seismic design categories B and C, equivalent lateral force is the most commonly used procedure. In seismic design categories D, E, and F, it is more common to see modal response spectrum analysis or response history analysis used. Structures must be designed for the effects both of lateral and vertical seismic forces in these design categories. And the magnitude of lateral seismic forces is determined accounting for the structure's inelastic response. Vertical seismic response forces can be determined either using vertical modal response, which is relatively uncommon, or using the very simple formula that you see here, where the vertical earthquake response force on a structural element is estimated as 20% of the short period spectral response acceleration, S sub ds, times the dead weight of the structure on the element. And this is applied both to elements of the seismic force resisting system as to elements of the structure which are not part of the seismic force resisting system, because every part of a structure experiences seismic forces due to vertical earthquake response. I've shown here an arbitrary spectral response acceleration coefficient expressed not as spectral acceleration versus period, but rather as spectral acceleration versus displacement. This is called an acceleration displacement response spectrum. Some of you that are familiar with the ATC 40 document will be familiar with this type of spectrum. It's basically the same as the standard spectral acceleration versus period spectrum that you're used to seeing. The primary difference is that period here is expressed radially. And so a line such as I show here represents a structure having a given structural period. And if you plot a response spectrum in this manner, and you plot the period of your structure, you can easily pull off what the elastic displacement response of the structure is and what the elastic force of the structure is, simply as the spectral response acceleration at the period of the structure times the weight of the structure. As I said earlier, we typically design our structures to exhibit nonlinear response. The nonlinear response of the structure that I've drawn here in the form of a pushover curve accounts for the fact that as a structure takes on damage, it softens and becomes less stiff and also experiences less force. And the effect of that nonlinearity is also to modify the spectrum that the structure is experiencing through the damping that inherently occurs as a result of that nonlinear response. The R, C sub D, and omega zero coefficients that we use to determine our seismic forces are approximations of the beneficial effects of nonlinear response on the structure's behavior. The R coefficient represents the reduction in force that occurs as a result of nonlinear response. And the theoretical elastic response of the structure divided by R sets the minimum strength required by the standard for the structure. The omega zero coefficient represents the peak response on the pushover curve relative to that specified minimum response in an approximate manner, and is used to design pieces of the structure that could be sensitive to overstrength, such as the column beneath a discontinuous braced frame or wall. And the C sub D factor is used to determine the inelastic drift of the structure as opposed to the elastic drift. Configuration and regularity, as I said earlier, is an important consideration in seismic design. ASCE7 attempts to encourage the design of structures with regular configurations, basically by forcing you to design for larger seismic forces if you have irregular structures. Structures are regular if they have a uniform distribution of mass, a uniform distribution of strength and stiffness, and continuous structural systems and a continuous load path. Some irregularities result in requirements to perform more detailed analyses and also to design for larger seismic forces. Some irregularities, as I've said, result in portions of the structure having to be designed for higher seismic forces. ASCE7 recognizes basically two types of irregularities. These are called horizontal irregularities and vertical irregularities. Some examples of horizontal irregularities are torsion and extreme torsion, in which the structure tends to twist in addition to shaking back and forth due to mislocation of the structure's center of mass and center of rigidity. Re-entering corners are another type of horizontal irregularity. They're important to consider because at the re-entering corner, there can be concentrations of seismic forces due to the response of the outstanding wings around that corner, and that can create damage in the structure, such as the crack that's shown here at the corner of the roof of this structure. There are horizontal irregularities that we call diaphragm discontinuities. These are most commonly large holes in floors and roofs. And then there is an out-of-plane offset type of horizontal irregularity in which the vertical plane in which lateral resistance is provided steps back from one level to another. This has found to be damaging of structures because the elements beneath the discontinuous element, in the case of this cartoon here, of a shear wall that is offset at the first level, can crush the elements that are supporting that discontinuous elements. One of the most important vertical irregularities is a weak or soft story. Very common in building structures, because architects like to have tall first stories to create a grand lobby and entrance space to buildings, and also commonly like to discontinue structural elements such as columns in these first stories. What such irregularities can do is result in a concentration of displacement and damage in the first story. And what you're seeing here is damage that occurred to the Olive View Hospital in Los Angeles during the 1971 San Fernando earthquake, because it had both a soft and a weak first story, and also had non-ductile detailing of its concrete frame. Another type of important vertical irregularity is an in-plane offset of the seismic force resisting system. The diagram in the middle left there shows a shear wall that tapers as it goes up in elevation. That's one type of in-plane offset. Another type shown on the diagram in the extreme right is a braced frame structure where the bay of bracing jumps from one area of the structure to another as you go up the structure. In determining lateral forces on a structure for design of the seismic force resisting system, it's important to understand the deflected shape of the structure, the weight of the structure, and the forces are going to be dependent on the location within the structure. And basically, the seismic design forces are determined as a function of the modal shape of the structure when in free vibration. This structure here, shown in first mode vibration here, obviously has more displacement as you go up in height in the structure. The result of that greater displacement in the structure as you go up its height is that the acceleration in upper levels of the building will be greater than at lower levels of the building, and therefore the forces experienced by the structure will be higher at upper levels of the building than in lower levels of the building. We start off in determining these seismic design forces by computing what we call the base shear force for the building, represented by the coefficient V. The total base shear is equal to a seismic response coefficient, C sub S, times the weight of the building. In the equivalent lateral force technique, the C sub S value depends on the fundamental period of the structure, the risk category of the structure, the structural system used. Chapter 12 of ASCE 7 gives a series of formula for determining the value of C sub S, and these formula basically replicate the different regimes of the smooth design acceleration response vector, as shown in this slide here. So for short period structures, C sub S is equal to the short period spectral design acceleration, S sub ds, divided by the quantity R, divided by the occupancy importance factor, I. For longer period structures, it's equal to the hyperbolic expression as a function of period that you see on the lower part of the slide. And for very long period structures, where we're in the constant displacement domain of the response spectrum, it's determined by a parabolic formula. For any structure, the C sub S value cannot be less than 0.44 times S sub dsi. And this is a historic requirement that actually goes back to the 1933 Uniform Building Code, which stated that no structure could be designed for less than 3% of its weight as a lateral force. That 3% has expressed itself now as the somewhat more complex formula, 0.4 S sub dsi. And if you're in a place where S sub ds has a value of 1, and you realize that we're now designing for strength rather than ASD, allowable stress design, and that strength forces are 1.4 larger than allowable stress design forces, you see that that is still the same 3% of a structure's weight. In seismic design categories E and F, where we're near to a large fault capable of producing large magnitude earthquakes and very large seismic forces, there's also a requirement that C sub S not be less than 0.5 times the S1 coefficient divided by R over I. And that latter formula typically controls the design of taller buildings. Once the base shear force V is determined, we determine the seismic forces at each level as a function of the mode shape of the structure, which is approximately represented by the formula that you see here, where K is a function of the structural period. In addition to determining the required strength of the structure, it's also necessary to be sure that the structure is stiff enough so that the drift is not excessive in response to earthquake. Drift checks are used to assure that non-structural components will not see excessive damage, to assure that the structure will not experience P delta instability in response to earthquake, and also to avoid pounding with neighboring structures. Story drift used to check these things in ASCE 7 is determined at a story drift level, which is computed as taking the maximum displacements at each of 2 adjacent stories and dividing the difference between those displacements by the height of the story, as illustrated in this cartoon here. Design story drift is determined as the drift delta sub I at each level, determined during application of the seismic design forces, amplified by the coefficient C sub D to account for the effects of nonlinearity, and divided by the occupancy importance factor I, and that must be less than the allowable story drift as given in section 12.9 of ASCE 7. We compute whether or not a structure is going to remain stable by computing The theta coefficient, shown here as the weight of the structure above each level, times the displacement of that level, divided by the seismic shear force in that level, the height of the level, and the C sub D coefficient. If the theta coefficient is less than 0.1, then a structure is deemed to be stable. If it's greater than 0.25, the structure is deemed to be unstable and must be redesigned. And if theta has a value between 0.1 and 0.25, then you can do explicit P delta analysis to determine whether the structure remains stable. Strength, in addition to determining strength and stiffness of structural elements in seismic design categories D, E, and F, it's necessary to determine if a structure is adequately redundant. If a structure is determined to be not adequately redundant, then the required strength of the structure is increased by 30%. Redundancy is considered sufficient if removal of any one element in the seismic force resisting sample, for example, a brace in a braced frame structure, does not reduce the lateral strength of the structure by more than 1/3, or does not create an extreme torsional irregularity. If neither of those conditions is correct, then the structure is assumed to be non-redundant, and seismic forces and strength of the structure must be increased by 30%. Once we have designed the various elements of the structure, including shear walls, braces, columns, beams, for the required seismic design forces, it is necessary to detail the structure per the requirements for the selected seismic force resisting system as contained in the reference standards, ACI 318 for concrete, AISC 341 for steel, TMS 402 for masonry, and the National Design Specification for wood. In addition to the requirements of those standards, you should also look at Chapter 14 of ASCE 7. Chapter 14 contains additional detailing requirements for some structural systems. The International Building Code does not actually adopt Chapter 14 of ASCE 7, and so you could design in conformance with the code without actually following the detailing requirements in Chapter 14. However, the ASCE 7 committee strongly recommends that you do pay attention to Chapter 14 because it contains detailing requirements that we hope that ACI, AISC, the Masonry Society, and American Wood Council will adopt in future editions of their standards. Illustrated here are what some of the detailing requirements are for some types of concrete systems. For example, special concrete walls shown on the left, or special concrete moment frame shown on the right. These requirements tell you the spacing of reinforcing and concrete elements, limits on the materials of construction and steel elements, special welding requirements in steel structures, special connection requirements in wood structures, and special reinforcing requirements in masonry structures. Once we've designed the structural system, following all of those steps, it's necessary to design the anchorage and bracing of non-structural components. In seismic design categories C, D, E, and F, all non-structural components must be attached to the structure using seismic design forces contained in Chapter 13, with some exceptions. Mechanical and electrical components in seismic design category C, except those that are deemed essential to life safety protection and which are assigned an occupancy importance factor of 1.5, are exempt. Mechanical electrical components in seismic design categories D, E, and F, mounted at floor level, having an occupancy importance factor of 1 and weighing less than 400 pounds, are exempt. That covers most furniture. Mechanical electrical components in seismic design categories D, E, and F, having an occupancy importance factor of 1, mounted at greater than 4 feet above the floor and weighing less than 20 pounds, and connected with flexible connections, are also exempt. The component importance factor must be determined, obviously, to determine if a component must be anchored or braced. Typically, the component importance factor, I sub P, is going to have a value of 1 unless the structure is required for life safety protection, for example, like a fire suppression system, or is required to contain hazardous materials. And ASCE 7 has a complete list of the types of components that fall into these categories. Components that are not exempt are required to be designed for the formula that you see here. This is a new formula introduced in ASCE 722. It is similar to, but somewhat more complex than the formula we've been using since the 97 Uniform Building Code. Looking at this formula in somewhat more detail, we see that the value S sub ds is a ground motion parameter, same as used to design the rest of the structure. The occupancy importance factor, I sub P, is dependent on the type of component, and the risk to life safety depends on its failure. H sub S is the height within the structure that the component is located at. R sub mu is new to the formula and is the ductility of the selected seismic force resisting section. C sub AR is a coefficient that relates to the likelihood that the component will experience resonance with the dynamic properties of the structure. And R sub PO is similar to the old R sub P value that we used in previous editions of the equation that relates to the ductility of the component itself. This formulation contained in ASCE 722 will result in reduced seismic forces relative to that we experienced in ASCE 716 for many components and increased seismic design forces for others. Designated seismic systems, those are systems or components with an I sub P of 1.5 required for life safety, required for the function of a risk category 4 structure. In addition to being anchored and braced for larger seismic forces, also must be certified by their manufacturers based on testing or earthquake experience data to be capable of surviving design earthquake shaping with acceptable performance. That nearly brings me to the conclusion of my discussion. There is a final chapter of FEMA P-749 that has some special seismic design topics. This includes a discussion of performance-based seismic design, commonly used for evaluation and retrofit of existing buildings and structures, and also commonly used in the Western United States today for design of tall buildings. There's discussion of design for tsunami loads, which has been required for structures in coastal zones since ASCE 716. Discussion of the use of soil structure interaction analysis as a means of more accurately accounting for how the soils present at a site affect a system's response. There's discussion of special protective systems, including how to design for seismic isolation and energy dissipation. And finally, a more detailed discussion of requirements for non-building structures. That completes my presentation, which amazingly enough, it was completed just about on time. And with that, we'll go to answering your questions. Thank you very much for your attention.
Ron, did you still want to do that last poll?
Say again?
Did you want to do the last poll?
Actually, I wasn't aware I had one, but sure.
You'll find out what it is when we do it.
I'll find out when it is when you all do.
Okay, great. So the poll question asks how you feel about seismic design criteria now.
So does it look really complex and you're not sure if you can do it? Do you think you understand it and what is new about the standard and can do it better? Or do you still have lots of questions?
Well, Ron, we definitely got a lot of questions.
Good.
Okay, it looks like most people have already responded, so I'll go ahead and close the poll and share the results.
Good. Well, it looks like we've been helpful to most of the attendees.
That's good. Okay, now let me dive into some questions. So we got a ton of questions. As I mentioned in my responses to most of the questions that came in, Ron will answer as many questions as is feasible. I think we got a whole lot today, so I'm not sure if he'll be able to answer all of them, but we will do our best to get through as many as we can. And then right before we get into the Q&A, I just wanted to go over a couple quick housekeeping items. So if you're eager to receive your PDH certificate, note that they're only provided for those who registered and participated in the live webinar. So if you're watching the recording, unfortunately, you're not eligible for a PDH certificate. You can expect your certificate within the next 4 weeks. And lastly, due to the large volume of participants, please be understanding that we can't make exceptions to our PDH policy. So now we'll get into the Q&A portion. If you have any questions that haven't been submitted yet, please go ahead and type them into the Q&A portal. And with that, Ron, I think we'll dive in. So first question, what is the fundamental source of a structure's nonlinear behavior?
The fundamental source is basically inelastic straining, which you can think of damage. In a concrete structure, it's going to be cracking and yielding of the reinforcing steel. In a steel structure, it will be yielding and buckling of the beams, columns, and braces in the structure. In a wood structure, it's typically going to be slip that occurs in the nailed interface between the sheathing of shear walls and the supporting studs. And a masonry structure behaves very much like concrete, of course. It'll be cracking of the masonry and yielding of the reinforcing steel.
Thanks, Ron. Okay, this next question, we got a couple of different ways. Why is a weak story considered an unacceptable condition? If a lower story has sufficient strength and stiffness, what difference does it make if the upper floors are stronger or weaker than the lower floor?
Well, it's an excellent question. Weak stories are considered an unacceptable structural condition simply because weak and soft stories can concentrate damage. If you have a regular structure, the amount of nonlinear or inelastic behavior that occurs in the structure gets distributed throughout the structure. So, for example, in a regular moment frame, we would expect yielding of the beam column joints throughout the structure. And that dissipates a lot of energy and helps to reduce the structure's response and help it survive. If you have a weak story or a soft story, you tend to get a concentration of the inelastic behavior of the structure in the columns, in the first story. That can be highly damaging of those columns because the columns support the weight of the structure above. That can result in collapse. So design of weak story structures, except in design categories E and F, is not prohibited, but you do pay a penalty if you have a weak story structure. You have to design the structure stronger.
Thanks, Ron. How can I learn more about how the chance of collapse is calculated for the maximum considered earthquake, the risk targeted MCE shaking?
Excellent question. First of all, in design, we typically don't determine the probability of collapse. We assume that if we're following the ASCE 7 requirements and the requirements of the reference standards, ACI, AISC, et cetera, that our structure is going to have the level of resistance to collapse that the standard intends, 10% or less for ordinary structures, 5% for risk category 3 structures, 2.5% for risk category 4 structures. There actually is a FEMA document, and Chiara, I hope you can remind me of the number of the document, that puts forward the procedures for determining what the actual probability of a collapse for a structure is. Basically, what the procedure is you create a model of the structure, and you subject that structure to a number of nonlinear response history analyses to that suite of motions, and to that suite of motions scaled upward until such time as the structure collapses for each ground motion. So you would start at a scale factor of 1, run the suite of motions, hopefully the structure doesn't collapse, then you would amplify those ground motions by an amplitude of 1.1, run it again, and maybe for a few of those motions, the structure will collapse. Then you'll increase it by a factor of 1.2, repeat that, keep doing it until the motions causes all of the structures to collapse. Then if you plot the number of collapses that occur versus the total number of motions that you've run as a function of the amplitude that you've scaled that motion to, you basically develop what we call a fragility curve. And that fragility curve tells you the probability that the structure will collapse as a function of the spectral response acceleration of the ground motion at the structure's fundamental period. And I've remembered now that the magic number is FEMA P695. You can download it for free from FEMA's website.
Thanks, Ron. So it was mentioned that risk category 4 buildings are designed to remain functional. Does the acceptable amount of damage vary due to the risk categories? So 1, 2, 3, 4.
Could you repeat that?
So the question, the participant was noting that when you talked about risk category 4, you said that those were intended to remain functional after an earthquake. So can you speak about, is there a different acceptable amount of damage across the risk category spectrum?
So there are different levels of acceptable damage. As I said during my talk, first of all, the primary performance goal of the building code is to avoid collapse, because collapse kills people. And we unfortunately saw that last week with the earthquakes in Turkey. When buildings collapse, you kill thousands of people. And so the primary goal of ASCE 7 and the building code is to avoid structural collapse in any earthquake likely to affect the building. And for risk category 4 structures, we want that to be a very small probability. We say less than 2.5%. For risk category 1 and 2 structures, we allow a somewhat higher probability, 10%, conditioned on a very unlikely earthquake, this maximum considered earthquake, that has a return period of a few thousand years. For risk category 4 structures, we do want to increase the probability that the structure will remain functional. Now, that doesn't mean we expect that a risk category 4 structure will remain functional following a maximum considered earthquake. But we expect it to remain functional for most earthquakes that will affect the structure. In terms of allowable damage for structures of lower risk categories, we expect the structure after it sees its design earthquake to remain standing long enough for people to be able to exit the building. We expect that damage to critical elements important for egress of the building, including stairways, doors, ceilings over exit paths will remain up so that people can actually exit the building. And we hope, but we don't promise, that the building will be able to survive aftershocks. And the likelihood of that decreases with the risk category. So risk category 3 structures are more likely to resist aftershocks than risk category 2 and 1 structures.
Thanks, Ron. So you spoke a little bit about ASCE 722. It's the new version of the ASCE 7 standard. So somebody asked, do the methods in the 2022 edition increase the size of the force resisting members and the cost, or is it just a better quantification of how to resist those seismic forces?
Excellent question again. The answer to the first part of that question, does it increase the cost? The cost is, it depends. And it depends on the location of the structure. In some places, the required seismic design forces are less. And in some places, the required seismic design forces more. The introduction of additional site classes, CD, DE, et cetera, help us to minimize that impact and will help to improve economy of structures. The intent really is not to affect the economy of the design, with 722, but basically to provide higher reliability in the way we design structures. The ASCE 7 standard is revised every 6 years, just as the ACI and AISC and TMS and AWC standards are revised every several years. Basically, the primary reason for revising these standards is to take advantage of lessons learned from earthquakes that have occurred since the last standard was issued, and to provide higher reliability in design. Some structures will cost more to build under the new standard. Some structures will cost less. Hopefully they will all perform better.
Does the acceleration obtained from the default site class spectrum, is it always bigger than the acceleration obtained from a spectrum based on the geotechnical engineer's site class?
Not always. If the actual site class at the site where the structure is being designed is the same as the default site class, so let's say you're designing a structure that's actually located in a site class E type site, and the period of the structure is such that the spectral values for the default site is equal to those for site class E, then it has no impact. But for most structures, the design spectrum obtained knowing what the V sub S for the site is going to be less than what the default site class is. And it can be significantly less, as much as 50% less.
Thank you. In an earthquake, a building may be damaged enough that its period has changed. Do we consider this to determine the building's performance for aftershocks?
So, first of all, ASCE 7 does consider this. Period lengthening is one of the reasons that structures responding inelastically tend to have lower total drift than structures responding elastically. And it's also one of the reasons why the forces experienced by structures responding inelastically is less than a structure responding elastically. So the R, C sub D, and omega zero coefficients all explicitly account in an approximate manner for period lengthening effects. Now, the question I think really was, do we account for this when considering the ability of a structure to survive aftershocks after an earthquake? And I'll say that we don't really do that through any standard procedures for evaluating structures, but that is certainly something that can be considered when you as an engineer are specifically evaluating a specific structure that has known damage. In fact, there have been some Applied Technology Council documents that have been developed that lead engineers through a process of doing exactly that, simulating in the model of a building the damage that has occurred, and understanding how that affects the building's ability to survive aftershocks. One of those documents was produced by the ATC 43 project after the Northridge earthquake of 1994. And there have been some other documents of that type as well.
Thank you. So in the structural systems table in chapter 12, where do the various R modification factors come from?
I'll say that largely those factors come from judgment and historic perspective. We started, when building codes first started specifying seismic design forces, and I could talk about this forever, they basically said that if you design for a lateral design force equal to 10% of the weight of the structure, it would be okay. We as a profession, not us personally, but we designed lots of buildings to those requirements, and they went through earthquakes. An earthquake in Santa Barbara in 1926, in Long Beach in 1933, in Bakersfield in 1952, and in many other places of the world. And we saw that some structures performed better and other structures performed worse. And we began to understand that the type of structural frame that was used to resist seismic forces affected a lot of structures' ability to resist earthquakes. And so in building codes of the 1950s, 60s, and 70s, we used K values to adjust the amount of seismic force that a structure was designed for, so that we designed some structures, for example, bearing wall structures, for larger forces than other structures, for example, moment frame structures. In 1988, the Uniform Building Code requirements were revised substantially based on a landmark ATC document, the ATC 306 document, and we threw out the K values and adopted R values that we use today. And those R values were literally calibrated back to the K values used in the building code of the 1970s. And then the number of structural systems were expanded greatly from the 5 structural systems contained in the 1976 Uniform Building Code to the 100 structural systems contained in ASCE 7. And engineering judgment was used to set R values to that wide expansion of structures. In recent years, researchers and engineers working on behalf of ATC and also the National Institute of Standards and Technology have conducted studies of different types of structural systems using the FEMA P-695 procedure that I described earlier, and confirmed whether or not the R values contained in ASCE 7 are appropriate. In some cases, adjustments have been made over the years, and in other cases, not. But largely, the R values are based, as I said, on judgment and historical precedent.
Thanks, Ron. I think we have, I'm going to throw in one more question and then we'll finish up the webinar. Why aren't energy dissipation systems and seismic isolation systems more common?
It's an excellent question. Actually, in some countries, notably Japan, New Zealand, even Chile, they are used much more frequently than they are in the United States. I think there are 2 basic reasons for that. One is they are expensive relative to conventional structural systems. And they impose some architectural constraints on the design of a building. And developers in the US are all about low cost and architectural appearance. So things that cost more and which impact the architectural appearance are not popular. And the other reason is that in the United States, fortunately, we don't experience earthquakes very often. And as a result of that, generally our development community is not very afraid of earthquakes. And so as a result of that, they are unwilling to invest the relatively modest extra money associated with the use of those systems. Perhaps with more events happening, like the recent earthquakes in Turkey last week, and I know we're going to have additional earthquakes in the United States, the use of these systems will become more popular.
Thank you, Ron. So we're all out of time. Ron, thank you so much for your presentation and for the Q&A session, which we got through quite a few questions. Many more remain. So I just have a couple of final words before we end the webinar. There is a survey link that pops up when you leave. We really appreciate if you fill out that survey because we use the information we get about webinar topics that you're interested in to shape the webinar program in the future. And know that you will receive a follow-up email, I think in 1 to 2 days, that'll include a link to the recording, a link to the handouts, and another link to the survey. So with that, on behalf of FEMA and the Applied Technology Council, I'd like to thank Ron for his excellent presentation. And I'd like to thank everyone for joining us today. This concludes the webinar.